So I'm going to do another example very similar to the previous example. So we've got a cliff right here, and we've got someone, a worker that wants to work on something that's hanging over here, but it's like over nothing. So what he does is he takes a long board right here and piles a bunch of bricks on it right here. Okay. And now uh, uh, um, what we have here is 180 kilograms worth of material right here. Okay, let's say the board has a mass M1 of 25 kilograms, and the center of the board is a distance of 1.1 meters from the edge here. So clearly that's the center of the board, and so these things are here. Let's say that the pile of bricks is 1.2 meters this way. And now we have a person here of mass M2 of 75 kilograms starts walking out here. So the question is, how far out can this person walk before this gives way and rotates like that? Okay. So we think about it and we say, okay, so what's happening here? We have a normal force pushing up right here because we have gravity pulling down. Now, the farther the person walks out here, okay, then what happens is the normal starts, the center of the normal starts moving closer and closer to the edge right here. Okay, now what's happening is we've got the cliff here. If we think about the board, free body diagram, we got M1G pulling down right there. Okay, that's a distance of 1.1 meters from the edge. Okay, this is my pivot point right here. Okay, so that's going to be a clockwise torque. We have the person, M2G, and there's some distance x over. That's also a clockwise torque. We've got the pile of bricks over here. That's pulling downwards here with a M bricks G force right there. That's a distance of 1.2 meters this way. So that is going to be a counterclockwise. So we have two clockwise and two counterclockwise. Okay, now it's not rotating. So if there's a normal force here, the normal force is going to be a clockwise. Okay, so what happens is that the normal, again, is whatever it needs to be. Remember, this is the nature of the normal force. It's whatever it needs to be. So that will hold it steady. So in other words, if the counterclockwise torque is bigger than the clockwise torque, the normal pushes upwards to steady this thing so that it does not rotate this way. It cannot rotate that way because there's a surface right there. Okay, but the farther the person walks outwards, the bigger the clockwise torque. And therefore, the less counterclockwise torque you need to balance. Okay, and so rather the less this clockwise torque is necessary to balance, rather. And so that means the normal gets closer and closer to the edge because remember the torque is going to be the force times that effective distance right there. Okay, all right. Now, eventually that reaches the pivot point. Okay, so that goes to 0. When that happens, then there's no more torque available from the normal. So if the person takes one more step further this way, the torque cannot be exerted any further that way, and so it cannot compensate for the clockwise torque, and at that point, the entire board rotates, starts coming down, and when it does, as this starts rotating upwards right here, then this force is now less of a distance over, and so now it actually has less of an effect. And so what happens is that this starts to try to slide down, which makes it even less of a distance, and eventually things go crashing down right here. Okay, so we got mass of the bricks times G, 1.2 meters. We got mass of the board times G at 1.1 meters. We got mass of the person times G at some X. And so we're going to say that the normal is out of the picture now because it's going to be right at the pivot point. If D is 0, it doesn't do anything. And so we can now say that the clockwise torque has to equal the counterclockwise torque. So the clockwise torque is going to be m1g times 1.1 meters, and it's going to also be m2g times x. The counterclockwise is going to be mass of the bricks times g times 1.2 meters. Well, the g's all cancel, okay, and so we look at this and we say, okay, then we can say